Hello children, this is once again Rupa Kuntala with some more examples of mesomeric effect where we are going to discuss the stability of allyl and benzyl carbocations and even the free radicals also and free radicals. Okay, that is carbocations and free radicals. I hope you all know the free radicals. The free radical means where the carbon is having the free radical means where the carbon is having the incomplete octet. That is less than 8, 7 electrons. Where carbocation will have also incomplete octet. That is 6 electrons. Carbocation is formed by heterolytic cleavage by loss of electron positive charge, whereas free radicals are formed by homolytic cleavage, equal cleavage, the bond, covalent bond cleaved equally. The both divided or separating atoms take their own electron and go back without any loss or gain. So free radicals are neutral. So we are now we are going to discuss the stability of allyl carbocation and benzyl carbocation. Okay, first we'll discuss the allyl. Okay, allyl. Now I hope you all know allyl carbon. Allyl carbon. Okay, so take the first is allyl carbocation. Allyl carbocation. Allyl carbocation. Allyl carbocation. So see here. What is allyl carbocation? First of all, allyl carbon. Remember, any carbon, okay, any carbon having the CC double bond or any carbon having double bond is called sp2. Is called as sp2. Okay, sp2, or you can say it is vinyl carbon. And sp2 carbon is vinyl carbon. And to this carbon, if you attach an sp3 carbon, what is sp3 carbon? This sp3 carbon will have 4 sigma bonds. 4 sigma bonds. Say it is CH3. Okay, propene. So this carbon is allyl. Or if it is having CH2 and a group is present Cl. Now, if Cl is removed, what is Cl? Electronegative group. Electronegative group. So when the CCl bond breaks, we know that automatically what happens is heterolytic cleavage takes place. That is, the bond pair is going along with this total bond is taken by Cl. Then Cl is removed as Cl minus. And who lost electron? This carbon. And the carbon is called as carbon positive ion, that is cation. This carbon is cation, carbocation. And what is this one? This is what? The carbocation is allyl carbon. It is allyl carbon. It is allyl carbon. So this is what? An allyl carbon. So here, this allyl carbon stability. This allyl carbon stability is explained by resonance. Explained by resonance or mesomeric effect. Why? Okay. Why? Because here pi bond is in conjugation with a positive charge. Positive charge. In mesomeric effect, the complete transfer of pi bond takes place towards a sigma. Towards a sigma, where the next will have a pi bond or a positive charge or an electronegative element which attract the pi bond. So this the shifting of complete shifting of pi bond, a complete transfer of pi bond in a conjugated system which is unsaturated is called mesomeric effect or resonance effect. And due to this shifting, the one molecule change into more number of structures. Means for one molecule you have more than one structure. So it is like an exercise. It is like an exercise done by a fat person. Okay, due to cholesterol, the person is having what? The problems of getting heart attacks like that. So the doctor will advise the person to do lot of exercise or brisk walk like that. So then what happens? The bad cholesterol will digest and the person will become healthy. So in the same way, we know that any unsaturated compound having pi bonds or charges is unstable. It has to increase its stability. It has to increase stability means it has to live for more time. Otherwise, it will consumed by any opposite charged ion means it will react. So to decrease the react, they have to increase their stability. So any system having conjugated any molecule having conjugate system, it is stabilized by mesomeric effect or resonance effect, where the pi bond shifts completely towards the sigma bond, where the positive charge or other pi bond or other lone pair is present. Okay, it is mesomeric effect. So this is allyl carbocation because formed from allyl chloride, allyl carbon. Okay, now this is one molecule we have. Now this will exist in two structures. This will exist in two structures. See how. Now for this, I can write one more structure. I can write one more structure. See here, this molecule. Okay, this molecule having this pi bond. This pi bond will shift. This pi bond will shift towards the sigma. Complete. Therefore, the curved double-headed, the curved arrow. Okay, so means who lost electron here? Who lost electron here? This carbon. This carbon is lost electron because the pi bond was the in between these two carbons. Means each carbon gives one electron by mutual sharing. But totally the bond is shifted. Bond means two electrons. Totally shifted to this CH2 and CH2 plus. So the CH2 will become neutral because the total bond is coming means an electron is coming. But this corner carbon is losing electron. So due to shifting of this pi bond, what happens? Electron is flowing in this direction towards CH2 plus. So the CH2 charge, positive charge is neutralized, stabilized, become neutral, and the positive charge is developed at the other end. Okay. So see here, what is happening? This structure converts into the structure. This double-headed arrow used to show interconvertible structures by delocalization of pi bonds or resonance. Okay, so we get here one more structure. So take this CH2. Next, single bond I'm writing. Sorry, here we have to write only. We have to write here only what is a CH because I was started with the ethylene. Now, okay, now it is a CH. Next, CH2 double bond. Now this pi bond is shifted here. So means this is electron deficient. Electron deficient. Okay, electron deficient. So what happened here? Now for one molecule, we got two structures. First structure and this is a second structure. So charge is shared by two carbons. First carbon and this carbon. So because of delocalization, the charge is dispersed, satisfied and shared by two carbons. Two carbons. Okay, stability increased. And see here, there are three types of allyl carbocations, like alkyl carbocations. We have three types of allyl carbocations, three types of benzyl carbocations. Okay, so obviously here, what is happening here? Towards the this positive end, the electrons are transferring, means electrons are added to this positive charge. So what is this effect? Plus mesomeric effect. So please remember that the stability of allyl carbocation or allyl free radical or benzyl carbocation or benzyl free radical is accompanied by plus mesomeric effect. Plus mesomeric effect. Okay, plus mesomeric effect. So here see, we have three different types of allyl carbocations. That is tertiary is there. Okay, tertiary is there. We know that tertiary is there. Secondary carbon, then primary carbon. So according to plus mesomeric effect. Okay, due to plus mesomeric effect, the tertiary allyl carbocation stable than secondary. Secondary stabler than this primary. I hope you know that what is primary and secondary. A carbon attached with only one carbon, primary. So this carbon is allyl carbon attached with only one carbon. It is primary allyl carbocation. Primary allyl carbocation. Okay. So for primary, How many structures we have seen? Two structures, and where the charge, positive charge is shared by two carbons. Now we'll make it to, secondary. We'll make it to secondary. Okay, secondary means a carbon attached with two different carbons. So now to this allyl, I will change this to secondary, means to this primary. It was with one carbon primary. Now attaching one more, one more. So since to this carbon, two different carbons are attached. Okay, so therefore it is secondary. Now here H and this is double bond CH2. Okay, double bond CH2. So it is one structure. It is a secondary allyl carbocation. So this structure will change into what? Two more structures. It is first structure. The second structure what? Same as this. This pi bond shift here. So therefore the loss of electron by this carbon. So this will become positive. And next this is CH becomes a double bonded and double bonded. And as it is here it is this moiety CH and this is double bond CH2. Double bond CH2 is second structure. So till here, how many carbons are sharing the charge? 1 and 2. Next, one more also possible. One more also possible. That is, if this now next, if this pi bond, which is also in conjugation with the positive charge, if this will shift here, what happens? Then one more structure is obtained. So what is the third structure? What is the third structure? In third structure, you will have the positive charge developed here. Okay, we'll see here. Okay, we'll see here. We'll see this structure. Okay, I'm writing the third structure. See here. So see here. I'm writing the third one. See, this is interconvertible. I want some space. I'll write here. Okay, so see if this bond is shifted. So what happens? I'll write first a carbon chain. 3 carbons. This is 1, 2, 3. Then these two down. Okay, now this is CH2. This is as CH. This is CH2. Okay, this is CH. And next, this is CH. And this one is CH. And this is double bond CH2. So now the positive charge was here. Now due to shifting of this pi bond, there is a loss of electron to this carbon. Therefore, this is positive charge and this is double bond. Okay, so this is third structure. So for secondary, how many structures are there? 3 structures. So in 3 structures, here different carbons, 1, 2, 3 different carbons are sharing the charge. Therefore, as these charge structures which have same electron density, okay, which are interconvertible by delocalization of pi bond with the lone pair or pi bond is called as resonance structures. Okay, conjugated structures which are resonance. As the resonance structures increases, stability increases. So, in the same way, in tertiary, what happens? The charge is shared by 4 carbons. Therefore, 4 more resonance structures. 4 more resonance structures. So, thus, it is what the stability factor due to plus Me effect. Allyl carbocations have order tertiary more than secondary, secondary more than primary. Okay. So, it is same in the case of a free radical. If you put the free radical here, okay, then same thing. So, in the carbocation, radical was there. In the free radical chain will be there. Okay, here also same free radical. So, in the case of carbocation and free radicals, due to plus Me effect, stability is tertiary more than secondary. Secondary is more than primary. Okay, the same is true for the both carbocations and free radicals. That is for allyl and benzyl. Okay, now we'll see for benzyl. We'll see for benzyl. Okay, see what is benzyl first of all. What is benzyl? Benzyl carbo. benzyl carbocation. First of all, you should know what is benzyl carbon. Okay, see better. Benzyl carbon is also an allyl carbon. Okay, it is your benzene. It is your benzene. In benzene, you see that every carbon is having double bond. So all the carbons of benzene are sp2, and any carbon attached to sp2, which is sp3, is called as benzyl. So if I write here CH2 and this is Cl, benzyl chloride, BENZYL, benzyl chloride. If the bond is broken unequally, heterolytic cleavage, the bond is taken by Cl as minus. So what is left? You got here CH2 plus. So it was sp3 carbon. Okay, it is sp3 carbon. An sp3 carbon attached to benzene ring is called benzyl. It's called a benzyl. Okay. Now here this carbon is attached with this carbon. Only one carbon. It's called as a primary. It's called as a primary benzyl carbocation. Primary benzyl carbocation. Primary benzyl carbocation. So this is primary. Okay, primary. Next, in the same way, you may have secondary and tertiary also. We'll see. To this carbon, if you attach one more benzene ring, means one more carbon is directly attached. Means to the carbon, two different carbons are attached directly. So means that is here. This is primary. Okay, 1, 2, 3, and this is here. It was CH2. I am replacing one of the H with one more benzene ring. Now this carbon is having two different carbons attached. It is secondary. It is secondary, and benzyl carbocation. Still this benzyl carbon having the positive charge. And next we'll go for the tertiary. Means this carbon should attach with three different carbons, not rings. Okay, because each corner contains one carbon. Okay, so this time we'll go for the tertiary. See, this is C. In previous you have seen that. To this, now replace the CH2. Okay, from the CH2, H is replaced by one more phenyl ring. Okay, benzene ring. So CH. Now this time it was CH2 plus primary. Now replace one of them with one more carbon, secondary. Then replace one more carbon. Okay, one more hydrogen with one more carbon, but still positive charge is present on the carbon. This is with one more benzene ring. Okay, it is tertiary. So obviously the tertiary is more stable than the primary, secondary and primary due to resonance effect or mesomeric effect. We'll see how. Okay, we'll see how. Okay, now in the case of this primary benzyl carbocation, this positive charge will shift to the two ortho position here and here. Two ortho positions and one para. Means in the case of this primary benzyl carbocation, the positive charge is shared by four carbons. Four carbons. One is benzyl carbocation. The next one, these two ortho positions and para. So four. As you increase one benzene ring, so the benzene ring contain two ortho and one para. So 4 plus 3, this will have the charge, means the positive charge. This charge is satisfied by or shared by, along with this 4, 3 more. That is this carbon. Okay, benzyl carbon, 2 ortho, 1 para. 3 plus 1, 4, and here 2 plus 1, 3, means 4 plus 3, 7 carbons. Whereas here one more ring is increased. So one more ring means 3 positions, means 7 plus 3, that is 10 carbons share that positive charge. 10 carbons share that positive charge. Okay, now we'll see the mechanism of this interconversion of the structures. Okay, so the primary benzyl carbocation is stabilized by plus mesomeric effect, because from the ring the pi bond is moving towards the positive carbon. So it is stabilized by plus mesomeric effect. Okay, plus mesomeric effect or plus resonance effect. Whereas minus ME effect, stability decreases. Okay. Now we'll see the mechanism how this stabilization takes place. That is nothing but conjugative mechanism, mesomeric effect or resonance effect. Resonance effect. Okay, see here. Okay, this is benzyl carbon having positive charge. Now, obviously, we know that the positive charge and pi bond are in conjugation. So this pi bond will move towards the positive charge. So this pi bond towards a single bond where positive charge is present. So therefore, you get a structure like this. You get a structure like this. These two bonds are undisturbed. There is no change in their position. Then the total bond is shifted from here to here. It was like this, now change it. So this ortho carbon will get a positive charge and the single bond will become a double bond. Single bond will become a double bond. Then CH2, as the bond is coming towards the CH2 plus means electron is coming. Electron is negative. So negative charge of electron plus positive charge will neutralize. So charge was at this carbon, now on the second carbon. First structure, this is second structure. Okay, second structure. The next, once again, this pi bond will shift here between the sigma. So means this para will develop a positive charge due to loss of electron. It is unchanged. It is newly formed, and this is double bond CH2. Double bond CH2. And next, one more structure. This is third structure. One more structure. One more structure. This time, this pi bond will shift here in between sigma bond, that is this para and beta. So new bond is formed here, this old bond, and this ortho will become positive, and this is CH2, which is neutralized. So this is what fourth. So in primary, the charge is shared by 4 carbons. So in secondary, 4 plus 3 because 2 ortho, 1 para is added, 7 carbons. In tertiary, 3 more, that is 10 carbons. So as much as resonance structures increases, as charge is satisfied by more number of atoms in a system, then what happens? The stability increases. Simple example, if any nucleophile means negative group attacking on this benzyl, it will search for what? This positive charge. But here the positive charge is no more there because shifted to ortho or para position. So nucleophile will try to catch at a benzyl position, but it's shifted to ortho and para. So means the nucleophile is confused, will not allow reaction. So therefore, the stability means the attacking of nucleophile will not takes place. Means the benzyl carbocation will take some rest to react with the nucleophile. Means till the charge is coming back to this CH2 plus, the nucleophile has to wait. Means it is making the nucleophile to wait means its a time of living is increased. So means the benzyl is not short-lived. Means though it is charged short-lived, but its stability is increased. So why it is stable? Because of resonance, mesomeric effect or mesomeric effect. Okay, prepare this well. Thank you.